All right, so this is going to be a walkthrough of the first exam from MA 158 for spring 2025. Okay, given f of x is equal to 3x plus 1, evaluate f of 4. Okay, so in this question, we're given a function f in terms of x, and it's asking us to figure out what that function is equal to based off of when x is going to be equal to 4. You can see this because we have that written here, f of 4, and then this is our function f with respect to x. A function f of x. And we know it's a function f of x because you can see on the right side here, we have x's in the actual equation. So in order to solve that, we just have to plug in 4 for x here. So just replacing all of the x's with 4's and then simplifying, and that will give us our answer. So first I'm going to write out the original function here. So f of x is equal to 3x plus 1. And then I'm going to rewrite it as just what is the function f going to be equal to when x is equal to 4. So to find that out, we just have to replace x with 4. So we end up with 3, 4 instead of x plus 1, and then simplify. And so from there, you end up with 3 times 4 is 12, plus 1 is going to be equal to 13. And so this is what f of 4 is going to be equal to. So this is going to be f of 4. And so the answer to this question is going to be C. All right, completely factor the given expression here of 2x squared minus 6x plus 4. So in this question, we're given a quadratic expression. I know it's quadratic because it has a degree of 2, and so that means that the highest exponent or power in the expression is 2. You can see that here because there's an x squared there. So that's what makes this a quadratic expression. So because of that, since we have an expression like that, we can factor it like the question says, and that's useful for other applications of whatever you're trying to do. And usually, when you want to factor something, you have to split it up into smaller terms, I guess. And usually you'd have an expression that takes the form of like ax squared plus bx plus c. And the given expression, in fact, does take this form. So you can see here clearly that a is going to be 2, and then b is going to be negative 6, and then c is going to be 4, as you can see like this. And so generally speaking, when you factor an expression like this, you want to come up with two values that multiply to your c value and add up to your b value, and then use those to come up with smaller parts. But that straightforward approach usually only works when your leading coefficient is equal to 1, or your a value is equal to 1. But in this case, our a value is equal to 2 instead of 1, so we're going to have to do a couple of additional steps beforehand before we can actually factor it. And the two main ways you can do that is by either factoring by grouping or by isolating this 2 and coming up with a new expression that allows you to do the thing that I mentioned earlier. And so with this question, you're going to see that you can't actually factor this by grouping. Usually you can. I mean, you can try to, but factoring by grouping doesn't always work. So we're going to have to take the other approach of isolating this 2. And I'll even show you, usually when you factor by grouping, you want to try to you want to split up your b value. So this value, you want to split it up into two smaller numbers that, like I mentioned earlier, multiply to your c value and add up to your b value. And so you'd end up with maybe an expression that looks like, I don't know, 2x squared plus, let's just say, I don't know, I guess wx plus gx maybe plus 4. And you'd want w and g to multiply to 4 and add up to negative 6. But you'll see that there aren't really any values that can do that for you. And so we're going to have to take the other approach of isolating 2 here. And so you'd end up with something that looks like this. And then since we isolated the 2, we'd have to divide the entire expression by 2 as well. So we'd end up with x squared minus 3x plus 2, like so. And now we have an expression where our leading coefficient is 1, and so we could take the original approach that I mentioned earlier of coming up with two values that multiply to this value and add up to this value. And so the two values that I'd come up with in this case would be negative 1 and 2. So yeah, negative 1 and negative 2. You'll see that when you multiply them together, so negative 2 times negative 1 gives you 2, and then negative 1 plus negative 2, when you simplify this, you'll end up with negative 3. And so that's how I know that those two values are going to satisfy this. And so then we can split this up into smaller terms that looks like this, where you have 2, and then x minus our first value, or plus our first value, which is -1, so it turns into a minus, so x minus 1, and then x minus 2. And from here, we can't factor any further unless we start bringing in some really weird tricks, so this would be about as far as you can factor this expression. So matching that up with the answer choices, that matches up the closest with answer choice C. Okay, given f of x is equal to 3x squared plus 2x, find and simplify f of t plus 1. So in this question, we're given a function f in terms of x, and it's asking us to figure out what that function is going to be equal to when x is equal to t plus 1, as written here. So what we're effectively going to be doing is we're just going to be replacing all of these x terms with a t plus 1. So first, let me write out the original expression here. So we have f of x is going to be equal to 3x squared plus 2x. And so what's going to happen when when x is equal to t plus 1? I'm writing it out like this to make it more obvious. And so then when you do that, you should end up with f of t plus 1. Since we replaced x with t plus 1 on the left side of the equation, we're going to have to do the same thing to the right side of the equation. So you should end up with something that looks like this, where you have f of t plus 1 is equal to 3 times t plus 1 squared plus 2 times t plus 1. So then all we have to do from here is simplify, and we'll have our answer. So the first two things I'm going to do is I'm going to expand this because we have, it goes to the second power. This parentheses term goes to the second power. And then I'm going to use a distributive property to distribute this 2 into the terms in this parentheses. So you should end up with an expression that looks like this, where we have 3 times t plus 1 times t plus 1 again, plus 2t plus 2. Because all we did is I just multiplied each of these terms by 2 because we have a leading coefficient of 2 here. And so then the next thing we have to do is, well, there's two things we're going to have to do. It doesn't matter the order that you do them in, but we'd have to also distribute this 3, and we'd also have to FOIL this. If you decide to distribute this 3 first, just make sure that you only distribute it to this first term. If you can't distribute it to this one too. The distribution would only apply to the first term. So personally, I think to avoid that confusion, it would be easier to FOIL first and then distribute. So that's what I'll do instead. So first, recall that FOIL, that's just an acronym that stands for first, and then outer, and then inner, and then last. And this is just an acronym used to describe the order in which you multiply things things in two binomial terms here. Binomial because we have two numbers. And so what the first entails is multiplying the first numbers in the terms together, so t times t, and then adding a term where you multiply the outer terms together. So we have this outer term and this outer term. So you'd end up with plus t times 1. And then you want to add a term where you multiply your inner terms together, so 1 times t. So you should end up with 1 times t. And then your last terms, so 1 and 1. So plus 1 times 1. So when you simplify this down, you should end up with t squared plus t again plus 1, which simplifies again to t squared plus 2t plus 1. Now make sure, since we had a 3 outside here, don't forget to bring that back in. So we're going to put that over here. And then also add these terms here too. So, well, I'll bring that down at the end because that we won't have to worry about that till the end. So first, let's also distribute this 3 into this term. So similar to what I did up here, I'm going to be distributing this 3. Oops, that's fine. Let me distribute the 3. So like I mentioned earlier with the distributive property, that's just going to be multiplying each of these terms by 3. So you should end up with 3t squared plus 6t plus 1. And then adding this term down, we have a plus 2t plus 1. So then all we have to do from here is just combine all of our like terms. And so we should end up with 3t squared plus 8t plus 2. And it seems like I made another mistake. Oops, hold on. I made another mistake. This is supposed to be 3t squared plus 6t plus 3. My bad. And so then once you do that, you should end up with, and I made another mistake. This is supposed to be a 2, not a 1. My bad. So then simplifying again, you should end up with 3t squared plus 8t plus 5. So this would be equal to f of t plus 1. And so then we can match it up with an answer choice. So we'd have, this would be equal to A. Okay, wow, I'm just realizing after editing this that I realized I circled the wrong answer. This is supposed to be F, not A. Sorry about that. Okay, find the domain of the function f of x is equal to x plus 7 over the square root of negative 3x. So before I proceed with this question, recall that a domain that defines, or no, not defines, like it's you're setting up a definition for a set of values that allows for the function to spit out like a valid real number. So basically, a region of values where the function is going to be defined when you plug those numbers into the variable of the function, in this case x. So to explain what I mean better, let me draw a graph real quick to give you an idea of what I mean. So let's say we have like some function, and it's a function that looks like this, where we have like a line here, like just a line that looks like this. So it starts at the y-axis here, and then it goes like this or something, and it ends. Hold on, let me get my eraser real quick. And let's say that it ends like somewhere around here. So let's just say it ends at like x is equal to 2, and then it starts at x is equal to 0. In this case, basically anywhere outside of this, so on this side and on this side, the function is undefined because the line doesn't continue into those parts. So with that in mind, what that means is that the domain of this function would be 0 to 2, because basically if you plug in any numbers between 0 and 2, you'll end up somewhere along this line. But if you plug in anything that's outside of 0 and 2, you'll end up outside, away from this line. And we know that the line doesn't exist in those regions. So that would mean that the function is undefined outside of that. So the domain would be from 0 to 2. And so with that in mind, we can use that to come up with the domain for this function here. So the two things I'm going to point out is, well, actually not two things. What we can do to solve problems like this is we don't really even have to do much math. We can use more conceptual things about the way math operators like division and square roots work to come up with something. So the first thing I'm going to write down is, notice how we have a fraction for a function, and we also have a square root in the denominator. With that in mind, we can point that towards, like, we know that we can't divide by 0, and we know that we can't take the square root of a negative number unless we want an imaginary number. So, but in this case, we don't. So so for the sake of this question, we can't take a negative square root, and we can't divide by 0. So let me write that down real quick. Can't divide by 0, and can't take square root of negative. With this in mind, we can come up with a set of values for x that don't break these rules that we came up with here. So we know, well, we have an x in the denominator, so we know that we can't put in 0 for x, because if we do that, you'd end up with the square root of negative 3 times 0, and that gives us 0, so we'd end up dividing by 0. And then we also can't take a negative square root, but we have a negative 3 here. And so that would mean that basically by default, this square root would give us, we'd be taking the square root of a negative number, unless we came up with a value of x that gives us a positive number. So that would mean that x would have to be another negative number to end up with like a negative times a negative to give us a positive. So in order for us to have that, we'd have to basically just, any negative number. So anything less than 0. So that would mean that this function would only be defined, this function, or no, I can write this out better. That would mean that f of x is only defined when x is strictly less than 0. Not less than or equal to, because in the case of less than or equal to, that would mean that we'd end up with the case with x is equal to 0, and we'd end up back at this issue where we'd have 0, which would give us a divide by 0 issue. And then it has to be a negative number because we need this to be positive. And in order to do that, we need to multiply a negative by a negative. So that would result in a domain of something that looks like this: negative infinity to 0. And so with that in mind, we can match that up with our answer choices. And our answer would be D. Now, if that approach of using those concepts, those mathematical concepts to come up with a conclusion doesn't make sense, I'll also draw out what this function would look like if you were to graph it, and that would hopefully give you a better idea of what I'm talking about here. So, similar to the example that I came up with here, how we saw that the function was only defined along this red line, and so the domain ended up being 0 to 2, we can use that same logic to show how the domain of this function is going to be from negative infinity to 0, because if we graph that here, if you were to graph the function for this question, you'd end up with something that looks a little something like this. You can plug this into Desmos if you want to see what I'm talking about. And so you can see how we end up with a vertical asymptote here, because we see that this red line, it gets closer and closer to the y-axis without ever actually touching it. But this red line is going to continue going this way, all the way into negative infinity, like all the way that way. So that's how you know that the domain is going to be negative infinity to 0. Because you can plug in any negative number into this function and still end up with an actual answer up until you reach 0 or close to it, and then you start to have some problems. And so, yeah, so that's why, well, visually speaking, that's why the domain is going to be negative infinity to 0. All right, so in this question, it's asking us to factor this abomination of an expression. So at a first glance, it might look like really, really ugly and might seem like really tedious, and you're going to just write a bunch of chicken scratch on your paper to get somewhere. But if you look more closely, this question is actually not that bad. What you really have to do is, well, the first thing I want to point out is there's a hint in the question itself. It's asking us to factor this and simplify it rather than just simply simplifying it. And so that kind of gives you an idea of like, maybe try doing some factoring instead of just foiling stuff and just multiplying things out and getting some giant blob of crap. So the first thing I want to point out is, well, yes, in this question, we are in fact going to do a little bit of factoring to get somewhere. The first thing I want to point out is notice how each of these things in parentheses, ignoring the exponents for a second, just pretend those aren't there for a second. You can see how each of these terms, we have an x minus 13 and a 7x plus 10 in each of the parentheses. So what you can do is you can pretend those are just singular numbers and factor things out. So similarly, like let's use I'm gonna use a more simple expression to give you an idea of what I'm talking about. Let's say we have like an expression that looks like, I don't know, 2x squared plus 4x plus 6 or something. What you can do is you can factor out a 2 here. We can see that all of these numbers are multiples of 2. So you can factor out a 2 and you'd end up with like 2 times x squared plus 2x plus 3 or something like that, right? So we can use that logic and do the same thing to this expression, except we're doing it with binomials instead of just singular numbers. So with that in mind, what you can do is we can notice how, well, since each of these terms has an x minus 13 and a 7x plus 10, we can take an x minus 13 and a 7x plus 10 out and come up with something factored. The next thing I'm going to do is bringing these exponents back into the mix here. You can see that we can take out a single x minus 13 because this goes to the first power and this goes to the second power. And then we can take up to 4 multiples of 7x plus 10 because we have a 4 here and a 5 here. And so we can't go any further than that, so you'd end up with something that looks like where you can factor out a x minus 13 times a 7x plus 10 to the 4th power. And when you do that, you're going to end up with a new expression that just looks like 7x plus 10 plus x minus 13. And if you're not convinced and see what I mean, you can multiply this stuff back into here and you'll end up back here with what I was talking about. So now we can consider this expression factored. And so all we have to do from here is just simplify this expression. And so that's just as simple as removing these parentheses and then just combining like terms. And so that's just going to end up looking like that's my laser. That's just going to end up looking like 7x plus 10 plus x minus 13. Which simplifies to 8x minus 3. So then, once you bring this stuff back in, you end up with a final factored and simplified expression that looks like x minus 13 times 7x plus 10 to the fourth power times 8x minus 3. And this would be the factored and simplified answer to this question. And so now we can just match this up with our answer choices, and this matches up the closest with answer choice E. So you can see how by factoring out, by taking out as many of these x minus 13 and 7x plus 10 terms as we can in the beginning, from there we were able to just come up with something where everything was in the first power here and then just add stuff together and end up with a nice expression like this instead of a foiled out mess of just garbage, I guess. But so the answer to this question is going to be E. Okay, given f of x is equal to 7x minus 3 and g of x is equal to x cubed, then find f composed of g of 2. So this question is basically just similar to the case of, like, let's say you have like a function like f of x and it's asking you what it is when you have like, it asks you to find like f of 2 or something. You know how like usually you just put in 2 for x and then simplify and you'd have your answer. This kind of question is just that kind of problem, but with a bunch of extra compounded steps. So just a bunch of extra steps. So let's build our way up to this thing over here. So starting with the case of just f of x. So f of x is equal to 7x minus 3. Let's say the question wanted us to find f of 2, then we'd say that f of 2 would be equal to 7 times 2 minus 3, right? Now let's say the question is asking us for f of g of x. So this. Or no, not f. F of g of x. This case, instead of substituting 2, instead of substituting 2 in like we did here, we're going to be substituting x with another function. So we know that in this case, g of x is equal to x cubed. So all we'd be doing is whenever we see an x on this side of the expression, we'd just be replacing it with whatever g of x is, which in this case, it's x cubed. So we'd end up with an expression that looks like this. F of g of x is going to be equal to 7 times x cubed, since that's g of x, and then minus 3, and then we'd simplify. And so finally, the next thing we have to do is focus on this thing over here. That's just this f circle g of 2 thing. That's just a really weird way of saying this, f of g of 2. So all we have to do from there is just substitute x here with g of x, but with 2 plugged into this instead. So let's start with g of 2. So we know that g of x is going to be equal to we know that g of x is going to be equal to, or g of x is going to be equal to x cubed. So g of 2, that's going to be equal to 2 cubed, which equals 8. And so then all we have to do from there is just plug 8 actually back into this thing over here. So then in the case of here, we'd end up with f of g of 2 is going to be equal to 7 times 8 minus 3. 7 times 8, that's going to be 56. So 56 minus 3, and you end up with 53. So this would be equal to f circle g of 2, or more normally speaking, f composed of g of 2. And so so the answer to this question would be D. Alright, given f of x is equal to 10x squared plus 8x minus 1, and g of x is equal to 1 over x, then evaluate 3 times f of 2 plus 6 times g of 1. So similar to if other questions that are asking you to just sub in like a value for a function, it's going to be that, but with a bunch of other steps on top of that. I guess just seeing if you really understand how that, that property works. So I'm going to start with the function. I'm going to start with f of x, and then I'm going to work over my way to g of x, and then I'm going to bring it all together and mash it together into a simple answer. So we know that in the case of f of x, we know that f of x is equal to 10x squared plus 8x minus 1. And it's asking us to find, in this case over here, we have an f of 2 term here. So we're going to have to figure out what f of 2 is. So plugging that in here, we have to substitute in wherever we see an x on this side of the equation, we're going to have to substitute in a 2 because we have f of 2 here. So you'd end up with an expression that looks like 10 of times 2 squared plus 8 times 2 minus 1. And so that's going to simplify to, well, 2 squared, that's going to be 4. So 10 times 4 is going to be 40. And then 8 times 2 is 16. And then minus 1. So 40 plus 16 minus 1, that's going to be equal to 55. Because we got 56 and then minus 1, so 55. So f of 2 is going to be equal to 55. Now let's move on to the case of g of x. So we have g of x, that's going to be equal to 1 over x. And it's asking us here, we have a g of 1 term. So similar to what we did with f of x, we're going to be replacing every x we see in this function with a 1 because it was written here. So we'd say that g of 1 is going to be equal to 1 over 1, which just simplifies to 1. So we know that g of 1 is going to be equal to 1. So now all we have to do is just plug that back into this expression. So we have 3 times f of 2 plus 6 times g of 1. We know that f of 2 is equal to 55, so this is going to turn into 3 times 55. And we know that g of 1 is equal to 1, so that's just going to give us 6 times 1. So simplifying this down, I forgot how to do multiplication. I think, what is this? 115? Yeah, this should be 115. So this equals 115 plus 6, which is going to give us 121. Wait, I forgot how to do, I think I made a mistake here. Give me a second. Oh, yeah, I see my mistake. No, this isn't supposed to be 115. This is supposed to be 165. See, yeah, I did forget how to do multiplication. My bad. So, yeah, so this should simplify to 171. So, ultimately, this question, the answer to what it was asking us is going to be 171. So, yeah, so this is going to be equal to 3 times f of 2 plus 6 times g of 1. So matching that up with our answer choices, the answer to this question is going to be B. So in this question, it's asking us to rationalize the numerator and simplify the given expression of the square root of 5 minus x minus the square root of 5 over x. So recall that when a question is asked, or when you're being asked to rationalize something, you're basically just trying to get rid of all of the radicals in your expression, I guess. So all of the square roots. And in this case, it's asking us to rationalize the numerator. So I'm going to be focusing on the top of our expression here. So everything that's in the top of this fraction, since that's what the numerator is. And now I'm going to show you how I'm going to get rid of the square roots. And the way to do that is you want to manipulate your function in such a way where you come up with a new expression that's equal to your original expression while still taking on like a new form. And the way to do that is the most straightforward way to do that is by multiplying your expression by some very unusual form of the number 1. And you'll see what I mean by that in a second. So first, let's write out our original expression here. So we have the square root of 5 minus x minus the square root of 5 over x. So now this is where I'm going to multiply by the weird version of 1 that I was talking about. I'm not going to be using the number 1 itself. I'm going to be using a different expression. And what I'm going to be using is I'm going to be using the numerator's conjugate divided by itself. Because when you divide something by itself, you end up with 1. The reason I'm going to be doing this is because since you're multiplying a thing that's effectively 1 by itself, you end up with the same expression but like taking on a different form. Anyway, what the conjugate is the conjugate is just it's just going to be like, let's say it's usually basically just a version of an expression with 2 terms but the sign flipped. So we have a minus here, so we're going to replace that with a plus. So we're going to multiply this by the square root of 5 minus x plus the square root of 5 over the square root of 5 minus x plus the square root of 5. And I hope you can kind of see what I mean here by a weird version of 1, because this is just something divided by itself. So this in itself is going to be equal to 1, and so we're basically just effectively multiplying our original expression by 1. Or yeah, by 1. And so that's why we can do this and still end up with the same expression. Now, the thing is, the reason why I'm using the conjugate, you might be thinking that we could just multiply this by itself, like the minus, but all that would do is just create more radicals instead of getting rid of radicals. And we're trying to get rid of radicals, or the square root signs. So that's why I'm multiplying by the conjugate instead. So now all we have to do is we just need to FOIL the numerator, our new numerator. So we end up with an expression that looks like, in parentheses, the square root of 5 minus x minus the square root of 5 times the square root of 5 minus x plus the square root of 5 over x times the square root of 5 minus x plus the square root of 5. And so out of force of habit, you might be tempted to just cancel these out, but don't do that because that would defeat the entire purpose of what I was trying to do in the first place here. So anyway, let's FOIL out the numerator. And so recall that FOIL is first, outer, inner, and then last. So multiplying the first terms together, these radicals are going to cancel because we're multiplying a square root by another square root. So you'll end up with, or I'll write it out. So 5 minus x times the square root of 5 minus x plus the outer terms. So the square root of 5 minus x times the square root of 5. And then minus the square root of 5 times the square root of 5 minus x minus the square root of 5 times the square root of 5 divided by our denominator. So yeah, x times the square root of 5 minus x plus the square root of 5. Now you can probably also see a little bit more why I use the conjugate, because you'll see that these two terms are going to cancel, and so that gives us one less term. And then these square roots are also going to eliminate since we're multiplying it by itself. And so you're going to end up with something that just looks like looks like 5 minus x minus 5 over the over x times the square root of 5 minus x plus the square root of 5. And then this can simplify because we have this 5 cancels with that 5, so you just end up with negative x over x times the square root of 5 minus x plus the square root of 5. And then additionally, the next thing we have to do is we just have to cancel out one more thing, because you can see that we have an x here and an x here. And so those x's are going to cancel. And so we're ultimately going to end up with a simplified expression of negative 1 over x times the square root of 5 minus x plus the square root of 5. So this is going to be our final rationalized and simplified expression. So the answer to this question, I believe, is going to be... Oh, wait, no. I said I was going to cancel the x, and then I kept the x here. This is what your final answer should be now. So yeah, so the answer to this question should be... I think F. Yeah, the answer to this question is going to be F. All right, given this piecewise function, this function f of x being a piecewise function, evaluate f of 0 plus f of 2. So similar to many of the other questions on this exam that ask you to substitute in something and into the function and simplify, this is going to take the same approach, except the only difference is since we're dealing with a piecewise function, that means that the function is defined as something different depending on what your value of x is, since we're dealing with a function in terms of x. So you can see here, like, we have a bunch of expressions here with boundaries, or I guess you could say boundary conditions attached to each of them. And so what this tells us is, like, let's take this 3x plus 7, for example. This tells us that f of x is defined as 3x plus 7 when x is less than 0. And strictly less than. Notice how it says less than and not less than or equal to. So strictly less than 0. That's going to be very important for this question, because that could trip you up and end up giving you the wrong answer. And then on the flip side, you can see here it tells us that f of x is defined as the square root of 3 when x is greater than 2 and less than or equal to 3. So basically what this tells us is our process of substituting in a number for x and then simplifying is going to be the same, but the expression that we choose here, of these four that we choose, is going to be different depending on what numbers we have. So in this case, it's asking us for f of 0 and f of 2. And so in this case, we're only going to be using this part of the piecewise function. The reason why is because it says that f of x is defined as this when x is greater than or equal to 0 and less than or equal to 2. Emphasis on the equal to part, because that means that it includes the 0 and 2 here, as opposed to this case where it has to be strictly less than 0. So this doesn't include the 0 case. So for f of 0 here, we're not going to be using the 3x plus 7. We're actually going to be using this because this includes the equal to thing. Same thing for the 2 instead of square root of 3. So it might be easy to end up with an expression where you could say that like a f of 0 plus f of 2. You might make the mistake and say that this is going to be equal to 3 times 0 plus 7 plus the square root of 3. This is wrong. Because that doesn't include the 0 and 2 case. What we actually are going to have to do is f of 0 plus f of 2 is actually going to be defined as 0 squared minus 10 plus 2 squared minus 10. And so, yeah, this is going to be what you want to do. And so when you simplify, you should end up with 0 minus 10 plus 4 minus 10. And then this is going to simplify to 4 minus 20, which is going to equal negative 16. So the answer to this question is going to be E. Right, so describe how the graph of the given function is a transformation of the graph of the original function f, so y equals f of x minus 4 plus 9. So basically, yeah, this question is asking us, like, how is the function going to shift along a graph based off of the manipulations that were given here. So the first thing I'm going to do is I'm going to draw a plane here, and this will make it easier to explain this. So looking at this point here, we have a x minus 4 and a plus 9 here. The first thing I'm going to do is I'm going to tackle this part, this plus 9 thing. The first thing I'm going to do is let's go back to the basics of graphing like a linear graph. So something that takes the form of like slope-intercept form. So you have something like y equals mx plus b, where b is going to be your y-intercept. So that's going to be where your line intersects with the y-axis, and then this mx, that's m, is going to be your slope. So if you recall from the way y-intercepts work, we know that, like, let's say you have something like, let's say we have a function of like y equals, let's just say 2x plus 3 or something. What that's going to end up looking like is you're going to have a graph that goes up 2 units. You're going to have a graph that goes up 2 units and then to the right 1, right? So something like looks like this. But then since our y-intercept since our b value is 3, so we have this thing here, that means that this line is actually going to intersect the y-axis at y equals 3, since our y-intercept is going to be 3. So this graph in particular is actually going to look something like this, where we have a line that looks like this, that goes like this at y equals 3, because that's our y-intercept. So similarly, in this case over here, we have y equals f of x minus 4 plus 9. This is going to be like the y-intercept thing I mentioned earlier. So this function is effectively going to have a y-intercept of, it's effectively going to be shifted upwards 9 units from its original point. Because you can see here, like the y-intercept here, this effectively, it's shifted up this red line up 3 units, up to the blue line. So the same principle applies here. Whatever function this is, it's going to shift the behavior up 9. So we know, so moving over here, let me zoom out a little bit. Moving over here, let me also graph like our hypothetical function f of x. And I'm going to use a pretty ugly line because it'll make it easier to illustrate what I'm talking about. So let's say we got something like this. Let's say f of x looks something like that. Since we have a plus 9 here, that tells us that with the y-intercept stuff I talked about earlier, it's going to shift up. This is also not to scale, by the way, so just use the labels I used instead. So this is going to be y is equal to 9. So now this tells us, so now we know that because of that plus 9, using the y-intercept stuff I talked about earlier, we know that the function is going to shift up 9 units. And then the next thing I'm going to do is I'm going to be focusing on this x minus 4 thing. It might be easy to think that with that x minus 4, that's going to shift the that's what that's going to do is that's going to change the horizontal shifting of the function. So this function it's still going to take the same shape. It's just that where it happens is going to be different. Since the plus 9 made it go upwards, that x minus 4 thing is going to make it go left or right. it might be easy to think that it's going to shift to the left because you have a minus here, but it's actually going to shift to the right. And the reason why is because what we're effectively doing is we're basically like, we're giving the x value like a reverse head start. I don't know if that's like the best way to put it, but like what this minus does, that minus is effectively, I guess, like, it basically forces the function to, I guess, overcompensate to achieve the same value because it's starting at a position like 4 lower, if that makes sense, since it's a minus. And so wait, but what that basically means is that you're going to need a higher x value to achieve to achieve this shape. And so what that means is since the x-axis is horizontal like this, I'll even label it so we got like x and y here. What that means is you're going to end up with a situation where you have like it's going to take more x to get this red shape. And so it's going to end up taking that red shape like further to the right of the x-axis. And so our final function is ultimately going to be something like this, where it looks something like this. So it's going to end up shifting up 9 units and then to the right 4 units because of like the overcompensating thing I mentioned earlier. And so yeah, so matching that with our answer choices, this is going to be answer choice 4 units to the right. Okay, B. Yeah, this is going to be B. Alright, so in this question we're given a piecewise function, and it's asking us to find the domain of said piecewise function. So recall that with a domain, that's just going to tell us a set of values for which that function is defined. So that means like that function is going to, within that set of values, that function is going to spit out a real valid number. Anything outside of that, and you'd get something undefined, some does not exist, something scary, something ugly, yeah. And so since we have a piecewise function, it's going to make things a little bit complicated since that means that the function is going to be defined as something different depending on the boundaries given to us here. So the first thing I'm going to point out is we can use those things to quickly come up with like a mock-up of what the domain could potentially be. So we know that the function is defined as the square root of x minus 1 when x is less than 0. So we can say right there, we can come up with a first condition of that would mean that would translate to negative infinity to 0 using parentheses instead of square brackets. Recall that parentheses, this is used for like less than or greater than. And then like less than or equal to, you would use that's not a square bracket, that's another parenthesis. You would use square brackets. And so since we have a less than here, that's going to give us parentheses here. And so then the next thing we need to focus on is the next thing in our piecewise function of just x, and that just says it's defined as x from when x is greater than or equal to 0 and less than or 4. So we're going to attach a union here because we're focusing on a different part of the piecewise function. So now we'd have a square bracket here because we're dealing with a greater than or equal to, like I mentioned earlier, and then a less than on the other side. So we're going to end up with 0 to 4 with a parenthesis on this side. So that takes care of this part of the piecewise function. The next thing we're going to focus on in this is this part, the x squared minus 9. We're going to attach another union, and it says that it's defined as x squared minus 9 when x is greater than 4. So that's just going to end up looking like 4 to infinity. Another thing I want to point out is whenever you're dealing with infinity, always you're going to want to use a parenthesis instead of a square bracket because infinity is not an actual number that's just infinity. It goes on forever. So whenever you're dealing with infinity, ignore what I wrote here, just use a square bracket instead. And so this is going to be our mock-up domain. The next thing we need to look for is we need to make sure that these conditions in the piecewise function are actually valid and give us like actual numbers. The reason I'm saying this is because upon further inspection, you might actually realize that this part of the piecewise function is impossible. Like it's never actually going to happen. And so because of that, this part of this mock-up domain that I came up with isn't even going to be there because it's not valid. And I'll show you why. So I'm going to use a graph to explain what I'm talking about. At a first glance, it's easy to say, oh, it's defined when x is less than 0 because that's what it says. But then when you actually graph what the square root of x minus 1 is, you're going to end up with something that looks like this. Or no, it's not that sharp of a turn, but you're going to end up with something that looks like this. And recall that with square roots, you can't take the square root of a negative number. And so the square root of x minus 1 is undefined anywhere past this red dot. So anywhere past here. So it's undefined here. So it tells us that it's the square root of 1 when x is less than 0. And so that means that this part of the piecewise function, that's talking about this, it's talking about this side of the graph. And so it's impossible for that condition to be true. And so as a result, that part of the piecewise function is never going to actually happen. And so as a result, this part is going to be the only part of our domain that's valid. And so what that ends up doing is that's just going to be so from there we can match that up with our answer choices. And so that gives us an answer choice. Well, looking at what I have here, doesn't look like it matches up with anything. I think the closest it matches up with is D. The thing is, I think there's an error there because that shouldn't be accurate, because it says that like this would only be accurate. D would only be accurate if it would only be accurate if x was defined as it was defined as x like below 0, 2, which it's not. So that's a little bit strange. Give me a second. Let me see if I can try to figure that out. If I had to guess, I believe I think this question assumes that this is defined that this is defined at x is less than 0, because in that case you'd have two different parts of the piecewise function that would be valid, and that would make answer choice D valid. The problem with that though is that's not actually the case. So but D matches up the closest with what I came up with. Other than that little discrepancy, this would be the general approach to solve a Prout question like this. So I guess for the sake of this, the answer would be D. Right, simplify the given expression. So we're given what looks like a pretty interesting fraction, but there is a way. There are ways there are ways we can simplify this. And so the first thing I'm going to focus on is I'm going to bring out a rule here. There's a fraction rule that you can apply that tells us that in the case of when you have a fraction of a over b over c, that's going to be equal to a over b times c. If you're not sure where that rule comes from, you can also just use the rules of the way dividing two fractions works, where we know that, like, let's say we have let's say we have two fractions. Let's say we have a over b divided by c over d. This would be the same thing as cross multiplying and end up with a over b times d over c. So similarly in this case, you could rewrite this. This could be rewritten as a over b divided by c over 1. And so with that cross multiplication, you'd end up with just a over b times 1 over c, which gives us a over b times c, as written over here. So now with that out of the way, we can start focusing on the first step in simplification. So we can say that 1 over x plus 1 over 1 plus 1 over x, that's going to be equal to 1 over x plus 1 times 1 plus 1 over x. And so now we can do some stuff to simplify the denominator here. And so in order to do that, what I'm going to do is you might think your first instinct might be, since you see two binomials here, to FOIL, but there is a better way to simplify this. The first thing I'm going to do is I'm going to rewrite this as 1 over x. This can be rewritten as x over x plus 1 over x, which equals x plus 1 over x. You can do this and you can merge the denominator together, because since we rewrote 1 as x over x, now it has the same denominator as this, and so you can merge it into 1, and you'd end up with something that looks like this. And so now we can end up just actually simplifying this into something that looks like this. So let me draw an arrow here. This can be rewritten as x plus 1 this can be rewritten as x plus 1 over x times x plus 1. And then this can be rewritten as x plus 1 over x times x plus 1 over 1, which simplifies to x plus 1 squared over x. Now bringing back our original numerator here that we have over here. So this 1, let's bring that back over here. And this is going to be our new fraction, something that looks like this. Recall going back to our cross multiplication stuff that I have over here, this can be rewritten as 1 over 1 times, 1 over 1 divided by x plus 1 squared over x, which can be rewritten as 1 over 1 times x over x plus 1 squared, which just equals x over x plus 1 squared. And so this would be the final simplified version of the fraction given to us. So matching that up with our answer choices, the answer to this question is going to be D. Right, given that f of x is equal to 8x minus 1 and g of x is equal to 3 over x squared, then find g composed with f of x. So this question is gonna be another case of just substituting stuff into a function and then simplifying. And there was another question on this exam that did something similar to this. So it's gonna be that, but just with a little bit of extra compound steps, I guess. So let's so the first thing I'm gonna do is to clear up some confusion. In case you're not sure, this notation over here, this is basically just asking like that's gonna be equal to the same thing as just that's going to be equal to the same thing as g of, okay. That's going to be the same thing as, sorry about that, my computer seems to be acting up right now. That's going to be the same thing as g of f of x. And so then with that in mind, all we'd have to do is we just have to plug in f of x. If we'd have to substitute the x in g of x with whatever f of x is, and then simplify. And so what this is going to end up looking like is like, let's go back to the case of like where you have like g of x is equal to 3x plus 2, and we want to find like, let's say g of 1. This would be equal to 3 over 1 squared, right? So similarly, all we're doing is in this case of g of f of x, we're just replacing the x, every time we see an x, we're replacing it with whatever f of x is equal to. So in this case of g of f of x, that's going to be equal to 3 over f of x squared, which is going to be equal to 3 over 8x minus 1 squared. And then all we have to do from here is, well, we don't have to FOIL it because looking at the answer choices, it doesn't have it FOILed out. So we can say just right away that the answer to this question is going to be D. All right, so this question is asking us to simplify another expression, but this case is just going to be a case of manipulating or taking advantage of the rules of exponents and radicals, I guess, and the way they behave at its core. So the first thing I'm going to do is recall that with the properties of radicals and exponents and stuff, this expression can be rewritten as just having like a bunch of smaller cube roots. So it's when you have something in one big cube root, you can actually split it up into smaller pieces where you can take the cube root of each part of the expression individually, so long as they're multiplied and divided with each other. And so since each of these parts are multiplied and divided with each other, we can rewrite this as the cube root of 64 times the cube root of x to the 6th times the cube root of z to the 7th divided by the cube root of y to the 6th. And so now from here we can start breaking down each of these parts individually. So starting with the first case of the cube root of 64, that's going to go to 4, because 4 cubed gives you 64, because 4 times 4 is 16, 16 times 4 is 64. So that's going to give us 4 here. And then the next thing we can do is whenever you're taking like a radical, or any sort of root of a variable to a power, that would be equal to like a fraction. So basically dividing this by the root, so 6 divided by 3. So you'd end up with x to the 6 divided by 3, and then z times z to the 7 over 3, and then y to the 6 over 3. And so then you'd end up with 4 times x squared times z to the 7/3 over over y squared. Now there is one more thing we can do with this z. We can split it up a little bit more actually. So actually what I'm going to do is I'm going to rewrite this as just the cube root of z to the 7th. And I'm going to use the rule of distributing radicals that I used earlier to get to this point in the first place and do it again on z here, so that we're not just stuck with z to the 7/3 power, because like that's not a very pretty number. So we can actually rewrite this. We can rewrite it as actually 4x squared times z to the 6th times z, and then attach an individual cube root, to each of these instead. Like that. I hope that makes sense. And then focus on these z's individually, and you should end up with something that looks like 4x squared times z squared times z, the cube root of z. Since this z is to the first power, that's as low as it can go unless you want to rewrite it as like 1/3. So you'd end up with the cube root of z and then y squared. And so actually that kind of looks like a 2, so I could write that better. And then that's supposed to be a 4. There we go. So this is just about as far as we can simplify this. And so matching that up with our answer choices, the answer to this question is going, and there's supposed to be an x here, my bad. The answer to this question is going to be D. All right, last question on this exam. We are given a nice quadratic function here. So given f of x is equal to x squared minus 3x plus 2, solve f of x is equal to 0. So this is going to be, I mentioned earlier in this exam, like how factoring can be used for various applications in math. This is going to be one of those cases where, let's say you're trying to find the roots of a function, and that's just the term used to describe like the case when you're asked to solve f of x is equal to 0. So the first thing I'm going to do is I'm going to write it out. So we got f of x is equal to x squared minus 3x plus 2 is equal to 0. So we need to find the values of x that satisfy this equation. So values of x that when you plug it into this, we're going to end up with 0. Now, looking at the rules of quadratic expressions are expressions with a degree of 2, which means that the highest power in the equation or expression is 2. So you can see that here with this x squared. So in the case, let's say you had like a cubic expression. So you had something like x cubed minus like 2 or something. This would be cubic because the highest power is 3, so the degree is 3. The reason this is important is because that's going to tell you how many possible values you could have that satisfy this equation. So since the degree of this equation is 2, that tells us that there's going to be up to 2 possible real numbers that you can plug into this expression that would satisfy this. And so there are 2 ways you can do that. Well, there's actually 3 ways. There's actually 3 ways we can solve this problem. And the reason I know this is because let me actually write another thing. We can see here that this expression takes the form of ax squared plus bx plus c. And so you can see here clearly that a is going to be equal to 1, b is going to be equal to -3, and c is going to be equal to 2. And then I'll write a 1 here to make it more obvious. And so with that in mind, since the leading coefficient of this quadratic expression is 1, there are 3 main ways we can go about finding our roots. We can either factor it, we can either complete the square, or if you don't feel comfortable with those tricks, you can just plug this into the quadratic formula and that will give you your answer. So I'm going to show all 3 approaches for this question. So I'll start with the factoring approach. So when it comes to factoring, the trick with factoring a quadratic expression like this is you want to come up with a number, 2 numbers that when you multiply them together, you end up with your c value. So in this case 2. And then you also have to make sure those numbers, when you add them together, you end up with your b value, which in this case it's going to be -3. So another cool thing is, since the leading coefficient is 1, we don't have to do any additional preliminary steps beforehand. We can just jump straight into what I was talking about. So I'm going to come up with 2 test values. Let's just go with Let's just go with -1 and -2. I know this is going to work because when you multiply these together, -1 times -2, that gives you +2. And then -1 plus -2, that gives you -3. And so that satisfies what I was talking about. It multiplies to c, and it adds up to b. And so now we can factor this, and so f of x is going to end up being equal to an expression where after you come up with your numbers here, so in this case -1 and 2, you want to come up with something that looks like f of x is going to be equal to like x plus a times x plus b. Or actually no, let me use different letters to avoid confusion. Let's just use x plus w and x plus g. So like we could say that this would be w and this would be g. So plugging those in, you'd end up with f of x is going to be equal to x minus 1, since it's negative, and then x minus 2, and set this equal to 0. Then from what we can do from here is we can look at these cases individually and split them up into two equalities, and that's going to give us our two answers. So we can split this up and say that we have x minus 1 is equal to 0 and x minus 2 is equal to 0, and then just solve for x on these cases individually. And so when you do that, you're going to end up with x is equal to 1 and x is going to be equal to 2. And so now this would be our answer to this question. And so the answer to this question would be A. So that's how you would solve this problem if you were to factor. There are other ways you can do this. I mentioned that earlier, that since the leading coefficient of this expression is 1, we can also solve this by completing the square, which is an alternate approach that you can use to get to the same result if that's what you want to do. And completing the square, it's similar to when you're factoring by grouping in the sense that you end up transforming this into an expression that has, like, how should I put it? Like you're gonna end up with more terms, and it takes a little bit of finesse. But if you feel like doing it, then if it's more comfortable to you, then you could go this way. So let me rewrite this here. We have f of x is equal to x squared minus 3x plus 2. With completing the square, what you want to do is you want to come up with a quadratic expression that when you factor it, you end up with where I mentioned here, like in this case, like we have an x plus w and an x plus g, like a w and a g value. You want to come up with a new quadratic expression that's equal to your original one here that gives you a w value and a g value that's equal to each other. Then so that's effectively what completing the square entails. So what I'm going to do is I'm going to write this out as x squared minus 3x. And then what I'm going to do is I'm going to square our 3 here and add and attach it. And you'd end up with, well, 3 squared is 9, so you'd end up with this expression. The problem is this is not equal to what we had originally here. So we need to do an additional step to make sure that it does end up actually, in fact, being equal to this. And so what you do is you put this in parentheses and then just subtract 7. And what this does is we basically just expanded this in such a way where we have a new quadratic expression where when you factor this, your w and g values, like I mentioned earlier, you come up with your w and g values that multiply to this number and add to this number. When you hold on, actually, give me a second. Actually, wait, I realized, no. Completing the square, it actually scratch what I said. For this question, actually, completing the square is actually going to be probably like an extremely it's going to get very messy. So just ignore what I said there. Actually, I'm going to jump straight to just the quadratic formula approach. Because you could say that's the safer approach if you're not comfortable with factoring. So recall that the quadratic formula, that's just going to be negative b plus minus the square root of the discriminant, which is going to be b squared minus 4ac over 2a. And from there, it's just a matter of just plugging and chugging your values here into this expression. And so we know that a is going to be equal to 1, b is going to be equal to negative 3, and c is going to be equal to 2. So when you plug it into this expression, you should end up with negative 3 plus or minus negative 3 squared, negative 3 squared minus 4a, or no, not a, 4 times 1 times 2 over 2 times 1. And then it's just a matter of simplifying this and coming up with two numbers from it. And you're going to end up with two numbers because of this plus or minus here. So after you simplify, you should end up with something that looks like 3 plus or minus 9 minus 8 over 2. And then this simplifies further to 3 plus or minus 1 over 2. And then we're going to come up with two fractions. We're going to end up with 3 plus 1, so 4 over 2, and 3 minus 1, which is 2 over 2. And then these are going to simplify to 2 and 1. And you can see that we end up with the same values that we came up with by factoring by using the quadratic formula. So the answer to this question, as you can see once again, is A, by using that approach. So those would be the two ways that you can come up with the two values for this question. So yeah, that's this exam.